Okay, welcome back. So this is our third lecture. We've done a lot of mathematical preliminaries, and where we left off last time was what I consider to be a reminder to you guys, Maxwell's equations in integral form. And what I'm betting is many of you have first encountered these at the end of your high school physics course. So your high school physics course, probably if it was an advanced placement course, went through all the mechanics of what each one of these equations mean, and then in a wonderful summary of that, they presented all of them together. And I'm also thinking that happened to you probably freshman or sophomore year in college physics again. And so this, for those reasons, because those are fairly elementary courses, given that this is a first-year graduate course, these are sort of where I choose to begin the course, at least the electromagnetics of the course. The nice thing about this is what I'm really saying is this is the equivalent of F equals ma in the dynamics course. So if I was teaching classical dynamics, mechanics, and I wrote down F equals ma, well, you'd all nod your head and say, yeah, I've heard of that. And the reason you've heard of that is just because you've hung out in the right clubs at night, the libraries mostly. Now these are four equations. They're a little bit more complicated equations, but the rest of the course will be teasing out what they mean. And this lecture was going to begin exactly that exploration. Okay, so these are integral equations which we're not quite as used to looking at and to working with, but that's okay. That's what they are to start with. I'll tell you kind of the way I look at these equations. There are four of them. That's not that big a deal. There are two electric fields, D and E. Okay, so there are two electric fields, D and E. And in this class, I'm going to be very judgmental and tell you that I like E a lot more than I like D. Okay? So one thing, the units of E, does anyone remember what the units of E are? Volts per meter. Volts per meter. And those are, for an electrical engineer, if you can talk in terms of a volt, you can forgive the fact that I have to divide it by a meter. Right? So a volt per meter is what you're thinking about. And if you think about a field strength of a volt per meter, you can take a 9-volt battery and take the fields, take the plus side and the minus side, and attach wires to it. And the wire has to be pretty long, right? 10 volts, 10 meters. You have to go 9 meters apart before you get a field strength between those two wires of a volt per meter. Okay? So that's a tiny, tiny, tiny field. But still, it is a volt per meter, and that's what we like. And so E is an electric field here, and that's measured in volts per meter. And you'll see that this is an integral. That's an integral, and it's an integral, a path integral, right? So once I do that path integral, what happens to my volts per meter? It becomes a volt. So the being able to do this one-dimensional integral in space takes that meter away, and so this left-hand side here is volts. And in fact, what that is that's volts around a closed loop. That's the summation of a voltage around a closed loop. Okay? Now, in circuit theory, what should the sum of the voltages be around a loop? 0. But it's not in this equation, is it? If this left-hand side is Kirchhoff's voltage law, the right-hand side means that it can change. There can be something in there. Right? It doesn't have to be 0. And the requirement is that there be this B field and that it be time varying. Okay? So that means we've got to look at the rest of the equations. I can't just look at this one equation in isolation. I've got to look at the rest of the equations. So I've said that D and E are electric fields. B and H are the magnetic fields. And I will use E and D. I will use E, and D will just tag along behind it. And I'll use H, and B will tag along behind it. Okay? What are the units for H? Amps per meter. So if E has units of volts per meter, and H has units of amps per meter, my goodness, that's really nice. That's a really nice situation where I've got amps and volts at my fingertip every time I write an equation with E and an equation with H in it. And volts have to do with static energy, and amps, moving charges, has to do with kinetic energy. Okay? But that's a chapter that we'll get to in a little bit. Okay? So volts. And now we see that the right-hand side of this equation is a magnetic field. So if I have a time-varying magnetic field, if I have a magnetic field that changes with time, well, first of all, if I have a magnetic field that is static with time, and I take the derivative of it with respect to time, I don't get anything. Right? So even if I have a B field and it's static, I have the sum of the voltages around this loop are equal to 0, and yes, circuit theory rules. But as soon as that magnet wiggles, as soon as that bar magnet wiggles back and forth at some appreciable frequency, and I have this time derivative, Kirchhoff's voltage law gets broken. Okay? So this term here pops. There's another term like this. This is not a derivative, but there's this term here couples into the rest of the equations, and I'll walk through that in a second. But the last thing I want to do is I want to give you a little example of this. And this example is getting harder and harder to give every year because fewer and fewer people remember this. But back in the old days, you used to have television sets that you didn't plug into the wall or into a cable dish. You had an antenna on them. And in the back was a little loop antenna. Be honest with me, how many people remember that in the back of a television set there was this little loop antenna? Oh, good. I get to keep my analogy for another couple of years. So have you ever wondered about that loop antenna, right? There was, in fact, a time-varying magnetic field that was broadcast from the television station. And this, I think of this antenna as almost like a butterfly net. It's a little net that's out there, and it's catching that time-varying magnetic field as it goes around that loop. And so the end of the loops, they didn't quite join up. It dropped across probably a diode or some mixer like that, or some even a preamp maybe. But they went into the set and they were just separated out. So the time varying magnetic field that was the signal that was broadcast by the television station was captured and converted into a voltage signal that followed the modulation of the magnetic field. Okay? So this equation here can be related by all means to Kirchhoff's voltage law. It tells you that Kirchhoff's voltage law is really a Kirchhoff's voltage approximation, but try teaching that to an undergraduate. So we have to dress it up and excite all the undergraduate students, of which you're no longer. And so we call it a law, so you guys remember it. And now you come around to a course like this and we tell you, we lied. It's Kirchhoff's voltage approximation. And you've seen it in action. If you remember these little loop antennas in the back of your old television sets, then that's exactly what's going on with this equality. The time-varying electromagnetic wave feeds an excess voltage around that loop. Okay? Also happens in motors as well. Okay? Now, so I have an electric field here. I have an electric field here. I have a magnetic field here, here, here. Oh, and I have an electric field sitting out over here. So let's move up to our first equation here and talk about that a little bit. Okay? This is an electric field, and it's related to a new term that I haven't talked about, which is charge. Okay? So rho is charge, and J is moving charge, current. Okay? So rho that just sort of hangs around on a street corner doing nothing, that's going to be sitting here. Industrious charge that marches down the street, that's the J, that's the current there. Okay? The way I look at these equations, D, B, E, and H are responsive to charge and moving charge. That's the way I look at these equations. Is that the charge and the moving charge are the forcing terms to this set of equations. So this illustrates that point. If I've got charge sitting here, then there will be an electric field because of that charge. If I have a charge, if I have a single electron here, there will be an electric field because of that charge. And in fact, you've probably in your minds, even though we're not working with spherical coordinates yet in this class, if I have a point charge, you probably are already imagining the radial electric field away from that point charge. Or if I have a charged plate of a parallel plate capacitor, there's an electric field that points away from that or towards it, depending on the sign of the charge. Okay? So this is telling me exactly the connection between charge and the electric field. And it's interesting, rho is in fact a charge density, so the units for that are coulombs per meter cubed. Coulombs per meter cubed. If I integrate over a volume, I get rid of the meter cubed, so this is just the total amount of charge. The total amount of charge will give rise to an electric field spread out across that area. And I think if you look at that, D is worth a coulomb per meter. Right, a coulomb per meter multiplied through by a meters. Coulomb per meter squared multiplied by a meters. That'll balance the units. Okay. Now, then I move down to the next equation, and the next equation looks very much like the other one, right? I have a funny little line with a loop in it. I have a dot n dA, d surface, and on the right hand side I have an integral across a volume. The only thing that's different is I've replaced the d with a b here, so I'm talking about a magnetic field. And I've replaced the rho with a 0 here. So there's nothing that will produce, according to these equations, there's nothing that will produce a B field in the same manner that a charge will produce a B field. Okay? So a static charge will produce an electric field, but there's nothing that works with the B field. Nothing to produce the B field like in the same manner that a static charge does. Another way to say that is these are really telling us something about the shapes. These are telling us something about the shapes that we might expect from electric fields versus magnetic fields. Okay? And so if I have my parallel plate capacitor and I've got direct vectors and lines of electric field that come off of that, in accordance with this law, or I have a point charge and I've got radial field lines away from the point charge from that, radial electric fields. There's no such thing as a point charge in magnetics. In other words, if you have a magnet, the magnet has both the north pole and the south pole. But in fact, I can isolate an electron and have it have one quantum of charge, of minus charge. And I can isolate a proton, and I can have one proton of positive charge. So I can work with a single particle that has a single charge on it in an electric sense, but as soon as I have a magnetic field or a magnet, I have to have both a north pole and a south pole. So if you think about the field lines, from the electric field, from the electron, it moves out, whereas from the north pole to the south pole, it wraps gracefully back around. So there's something orthogonal about the D field and the B field that comes just from these two equations. There's something orthogonal between a D field and a B field, between a magnetic field and an electric field that comes out of these two equations if you shake them hard enough and look at them that way. Okay? All right, so these are the simple equations of statics. And these two equations here create some more interesting effects. Okay? Now, if this is charge producing an electric field here, take a look at this guy here. This is moving charge or current, a stream of current that gives rise to a magnetic field. So this moving charge here, if I can capture all this pipe of charge, this pipeline of charge, if I can integrate across the area of that pipe and capture all the total charge, well, that's equal to a magnetic field around that pipe, around that wire. Okay? So static charge gives rise to an electric field. Moving charge gives rise to a magnetic field. Okay? And again, the integrals there are just allowing us for bookkeeping and also allowing us for the vector components of how H relates to where J is and how D relates to where rho is sitting. Okay? So both the bookkeeping and in particular the shape of that is, or the shape of the field lines come from the integrals. Okay? So forcing term to this, forcing term to this. Okay? Now, if in addition I wiggle for example, my charge, I modulate my charge at some frequency, gigahertz, pretty fast, faster the better, because of these derivatives. If I wiggle this, then I also give rise to two other terms. And these two other terms are time derivative terms. Time derivative of an electric field to time derivative of a magnetic field. These are the coupling terms. These time derivative terms are the coupling terms in Maxwell's equations. These time derivative terms are the coupling terms. So a time-varying current gives rise to a magnetic field. That magnetic field happens to be time-varying, so it produces, this integral is no longer zero. It drives an electric field that's time-varying, which makes up for this guy here. Okay? So these two terms, the time derivative, beginning with J, creates a coupling back and forth between these guys here. Okay? In light of that, why is that minus sign there? Pardon? Maybe that's the name of it. But that doesn't answer why it's there. Why is that? What is that minus sign doing there? If I've got this loop going back and forth across all those terms.
It's the clockwise.
Pardon?
The field is clockwise. I mean, your sign there showing anti-clockwise, right?
Well, I'm not mentioning. I'm just working through the terms of the equations. So J will come to there will come to there will come to there will come to there will come to there, and all the way back through it. And if that feedback happens in a positive manner, then I get instability. These equations become unstable. And so minus sign here, it's often referred to as a back EMF. the back EMF, that acts to stabilize it or fight against the feedback loop. So that minus sign actually has a physical significance as well. Okay? We're going to do the same thing when we convert these equations into differential equations. We're going to go do the same guided tour of these. But I wanted at least to begin to give you a flavor of the physical interpretation of Maxwell's equations. Okay, and some examples. So for now, to summarize, charge measured in good old coulombs per meter cubed per volume. Then you integrate. Amps per meter squared, actually. Okay, for J. So charge and moving charge, current here, giving rise to a magnetic field, H. We like that one, that's amps per meter. So we're going to figure out a way to take these other guys here and write them as H, as H's. But these are perfectly good magnetic fields as well. Okay, but I just like H. And then we also have electric fields, E and D. And E is kind of nice because it is volts per meter. Okay? So that's how you can you can get very much lost in the details of these, and that's sort of if you blur your eyes, squint your eyes a little bit, that's how we might look at that.
Dr. Maxwell.
Yes, sir.
So there is the electric field and magnetic field between electron and photon, right?
Say that last piece again. There's an electric field and a magnetic field.
Between electron circling around the photon, right?
Circle. If I have an electron moving in a circle, then because it's moving, it will give rise to an to a magnetic field, and also to an electric field as well.
So we can define those fields by those last two equations.
We can. Well, we'd have to consider all of these equations at the same time. Okay. One more thing about the forcing terms on this, the charge and the moving charge. In my picture, the way I look at this, this guy here is very important. This is the antenna term. Okay? This driving term is the antenna. So if I want to, we talked about the receiving antenna. If I sit back to the broadcast television station, what I want to do there is I want to arrange an antenna, a shape of metal, a squiggly shape of metal. And onto that shape of metal, I want to toss a bunch of current, a bunch of charges that dance and skitter around on top of that metal. Follow the curves of the metal and follow it in the time at which I pump it onto that metal surface. What I've done is I've defined J.NDA in time and in space by the metal surface and by the time at which I feed that metal surface. That's my broadcast antenna. And that broadcast antenna is what gives rise to the D and the H. Okay? So I don't want to think that your electron, your single electron spinning, beautiful physics toy problem. Right? It's beautiful little physics toy problem where you get down and you figure out all the math of that. Supposing the real world intervenes and I squash that circle into an ellipse. Supposing I tell you that a single electron doesn't really give you a heck of a lot of field, and I want to shove several Avogadro's numbers worth on you. Okay? So all of a sudden I've got an engineering problem. And so for that reason I want to look at these I want to relook at these equations in a more general way, but also a way that we can that's tractable for more complicated problems. Okay? Having said that, my favorite example, I'll use it a million times, is to take a little electron and to glue it onto a string, onto like a fishing line, and dangle it in a field and see what happens to it. Okay? My little test charge. Okay? Now, let's see. What do I usually like to do next? Oh, I know what I like to do next. Okay. We also looked at two integral equations last time. Last week we spent on on a very quick review of some vector calculus, just almost really to get your mind working again that first week of school. Also, I think to introduce you to my really strange notation. So these two equations here are really quite interesting. Notice that I have a closed loop equation here. And I've got some closed loop equations here. Right? And notice here, I've got some closed surface terms here. And I've got some closed surface terms here as well. Okay? So I can apply the divergence theorem to these guys here. And I can derive Stokes' theorem, or I can apply Stokes' theorem to these two terms here. Okay? All right, I'm going to have to flip back and forth, sorry. So what I've done is I've written down my divergence theorem in red. My notation is horrible, and I apologize for that. Let me change this just a little bit to surface. And now there's no hiccup between the S and the A. Okay? So now I compare these lines here, and I have everything almost exactly the same. Except for my arbitrary vector A, I have my electric field D. And so I can write the left-hand side of this as the divergence of D across a volume. And that's still equal to the right-hand side because I haven't touched that, which is the integral of the charge across that volume. Now, if you think about this, this is a volume, and this is the surface that contains that volume. Do you remember my Diet Coke can? That started out being a beer can, but ended up being a Diet Coke can? I was sad about that too. So the volume of that Coke can is defined by the surface of the sides of that Coke can. And so this surface has to be related to that volume. And this volume has to be related to that surface, and so these two volumes have to be the same volume. They have to be the same volume. And so at every point on this, what goes on inside that, well, let me just collect all the terms. So if both those sides are the same integration, I'll just do whatever's inside of that and do one integration. But notice I have an integral across an arbitrary volume, and that all has to sum out to equal to 0. The only way for that to happen is at each and every point inside that volume, this integrand has to be 0. And so by logic, divergence of D must equal rho. Oh, thank you very much. Yes. Okay. So this line of using the divergence theorem allows us to rewrite Maxwell's equation in integral form into Maxwell's equations in a Maxwell equation in differential form. Along the way, it also gives a little bit more guidance as what we mean by a divergence. There's some quantity of charge that gives rise to a flux or a divergence of an electric field from that charge. Okay? So as we talked about last week, we now get yet another physical example actually in the field of what we want to study for what the meaning of a divergence is. Okay. And if I look at this is now a differential equation, first order, in space, partial, with a forcing term. Rho is the forcing term, the driving term. It's a simple differential equation, but I'm sure we can find some rhos that kind of make our life a little bit more interesting. Now we've thrown away information. We've thrown away information. The good news is we've gotten away from an integral equation, and we now have a differential equation. And we are much, much, much more experienced at working with differential equations than we are at integral equations, right? We are much more used to that. And that's the reason why we really like differential equations. That's why we're going to manipulate differential equations from here on out. Practically from here on out. Okay? The bad news is this equation held in macroscopic space. This equation held always in macroscopic space. And I could do an awful lot in that macroscopic space to mess it up, and I would still have this equation hold. So now when I go to this equation holds only at a point. Because the way I've manipulated my integrand, I've said that this integral will equal 0 if at every point this is equal to 0. So when I solve this equation, I solve it for 1 point at a time. And this equation takes into account any amount of complexity or sophistication. In particular, if I take a look at this sort of space that I'm not allowed to move too far from, I can say, well, this point here is the same material as here. It's about the same look and feel as this point here. So what I can do is I can sort of solve the differential equation for most points in this little area. Where I fall down or where I trip my toe is what happens through the desk. What happens through the desk. Because I've solved up here in air, and now all of a sudden I'm solving it in some fake kind of a wood. So what happens to that field as I move from air across the boundary into the wood? And that's the kind of question that I lose when I go from here to here. That's the kind of question that I lose when I go from here to here. So we still need to come back into here, and we still need to pull that information out so that we're able to solve our differential equations here, solve our differential equations in this fake wood, and then match up the boundary conditions right at the boundary. Okay? So I'm making some notes on the side of this. This one says macroscopically. You may not be able to believe that, but it's what it really says, or what I intend it to say. And this one says at a point. Okay? This one says at a point. Now I don't want to burden you. If I do this guy here, and I write that down on the top, and I go through exactly the same construction, exactly the same mathematics, I come up with that equation. Okay? So what I'd like you to do in your notebook is leave, let's see, 1, 2, 3, 4, 5 lines. 6, maybe. And I want you to repeat this whole exercise to get divergence of b equal to 0. I'm lazy, but I'm also going to tell you it's a really good exercise for you to follow. Okay? All right. So what I've done is I've taken this equation here, and I've gone to a Maxwell's equation in differential form. I've taken this equation here, and I've converted the integral equation into a differential equation. And I've done that using the divergence theorem. Okay? And what I'll now do is I'll take these guys here, and I'll convert them using Stokes' theorem to an equation in differential form. Okay. Okay, so I've written down Stokes' equation, and here's my electric field equation. And notice that this is a closed loop here, and this is a closed loop here, so I can rewrite this guy as the curl of E across a surface, and that's going to equal the same right-hand side as it did before. Now I collect all the terms. This loop is related to this surface, or this surface is this loop is the perimeter of this surface. This loop is the perimeter of this surface. These two loops are the same, so these two surfaces are the same. So I can collect all my terms. Watch that minus sign. Make sure I didn't mess it up. We now know that it's physically important. It would be a shame if a nice stable set of equations, just because I messed up, become unstable. Then all of electromagnetics won't work and probably have devastating effects on life as we know it. It's a funny thing about stability. Do you ever wonder about that 1 over r squared in a gravitational force? If that was 1.99999 versus 2.000001, neither of those would lead to a stable universe. The fact that it's magically 2.000 forever is pretty profound. And that's the same kind of stability that we're talking about here as well. Okay, I digress. So this whole thing has to be equal to 0. The best way to do that is to let the integrand equal to 0. So the curl of E is equal to minus del by del t of B at a point. And our other equation here can also be reduced to that equation. I'll remind you of that in just a sec. So the same manipulations that I've done here to convert a macroscopic integral to an equation that holds at a point, a differential equation that holds at a point, can also be done with this long equation here, where h is the star of the show instead of e. Do this manipulation, you'll have the curl of h across the surface. Instead of just the dv dt term, you're going to have the del d del t term and a j. Both of those are on the same surface integrals, so they'll just add up together and give you a new right-hand side. Okay? So we began with 4 Maxwell's equations in integral form. We now have 4 Maxwell's equations in differential form. And the reason we do that is because our familiarity with solving differential equations is much, much stronger, much more ingrained than solving integral equations. And if you think about all the integral equations that you did in undergraduate physics, and perhaps even undergraduate electromagnetics, you looked for symmetries so that you could find a surface of the electric field that you knew or pretty sure the field was constant across, so you can pull that out through the integral. Do you remember doing that kind of thought process? Some of you are politely nodding yes. I appreciate that. But that kind of insight robs you. That if you rely on things that are too symmetrical, it robs you of the ability to do really preposterously interesting engineering fixtures. Okay, so that's why we want to play with Maxwell's equations in integral form. And similarly, there are 4 of them. There are 4 of them, and we'll go through them at length another time. But we've got 2 divergence equations. Divergence of b is equal to 0. Divergence of d is equal to rho. We've got 2 curl equations. Curl of e is equal to minus del by del t of b. The curl of h will equal del by del d of t plus our forcing term j, our antenna term. Okay. Divergences are a way of taking a vector field. We dot it with our del operator. Do you remember that from last week? And what do we get? We get a scalar. And in fact, look at the right-hand side. Rho is a scalar. Right? A scalar field of charge. How many electrons do I have over here? How many electrons do I have over here? How many electrons are piled up over here? That's a really nice example of a scalar field. I think somebody emailed me over the weekend and said, give me some more examples of a scalar field. And that's a really nice one, right? Is that rho changing, piling up over here instead of over here? These fluorescent lamps have a definite current distribution inside of the charge distribution inside of them. There's a big clump of positive charge, a long drift of negative charge. So if you look through there, if you map there, you'll have a very rich function of rho. Unfortunately, there's a scalar function of rho. The right-hand side is scalar. The left-hand side is scalar. The left-hand side is scalar. We know that 0 is a scalar 0. Okay, so these 2 equations, they're perfectly good equations, but they're only scalar equations. Okay, these 2 equations, curls, another first derivative of the vector fields. Those are vector equations. So these 2 equations, this equation has 3 scalar equations inside of it. This equation has 3 scalar equations inside of it. So these equations are 3 times as good as these equations. And what I mean by that is they hold 3 times the amount of information. These hold 3 times the amount of information as measured by scalar fields as these equations do. Okay? You can't forget about these equations. These are darn good equations, but they will be overshadowed in this course by these two equations, for the very simple reason that these are vector equations and preserve the vector nature of the electric field and the magnetic field. Okay? Any questions?
Does the macroscopic still apply to this one? Is that a point?
These are yeah. As soon as I did this step of saying that this macroscopic equation will hold when every part inside this integral is equal to 0. Those are the magic words. Those are the magic spell at which I move from a macroscopic picture to a point. Okay, and so that's a very, very important piece. So when I collect these terms under that integral and I say this equality holds whenever this guy is always equal to 0, that's why I'm able to write that boxed equation. So yeah, I've taken that macroscopic element out of it. But now we're going to patch it back in. Now we're going to patch it back in because one of the things we have to do we have to figure out about the boundary conditions. So it's all, again, as I was saying before, hand waving before, it's all perfectly well to solve point by point by point by point by point, as we do with all differential equations, as long as everything is in the same material, for example, or nothing has changed too much. But and if I'm inside this desk, I have the same situation. The fake wood is more or less the fake wood all the way through the desk. So I can solve my differential equations out over here. I can solve my differential equations inside this material. And as long as I know what's happening at the boundary of that material, I can connect up those two solutions to the differential equations. Okay? But I need to know what happens on the boundary in order to be able to do that. So just a reminder that from a mathematical parlance, we must solve the differential equations subject to the boundary conditions. Okay? Now, the first one, I'm going to have a material 1. I'm going to have a material 2. On top of that material, I can have some charge, and I can have some moving charge. I can have some static charge, rho sub s, on the surface. Is that better? And I can have some current that flows along the surface of the current on the sheet. In fact, it's interesting. Most of the current will flow right between the boundaries of a metal and air, for example. We'll talk about why that's the case, but you find your charge on the surface. Find your current on the surface. So it's not preposterous to say that that's where that's living. And I have a material 1 and a material 2 floating on in there. And what I'm going to do is I'm going to drop a little construction across the boundary of that. And this is my little loop. I'll label my vertices A, B, C, and D. And what I've developed here is this line integral here, E dot dl. Okay? I've developed this little E dot dl. So I can now move my electric field and do my line integral from A to B, B to C, C to D, and D back to A. Okay? Now, this right-hand side here, we've talked about that as well. This is my little butterfly net, or my little loop antenna, that whatever B field flows through this, is going to add all that back up, and I'm going to have, as I walk around this loop, when I go from A to A prime, just right to there, I'm going to store up the amount of B dot NDA, its time derivative, that I've caught through that. If I make this loop bigger, I'll catch more magnetic field. If I make this loop smaller, I'll catch less magnetic field. Right? So in some sense, the strength of that term there is going to depend on the area that I'm going to be looking at. But I really don't care what happens up in here, up in here, up in here. I don't really care what happens up here and here. I care what happens exactly at the boundary conditions. I care what happens at the boundary conditions. And so for that reason, I'm going to take my B and my C and I'm going to put them really close together. And I'm going to take my A and my D and I'm going to go put those really, really close together. Okay? And when I do that, I run out of butterfly net. I run out of loop antenna. My right-hand term goes to 0. Okay. Now this line integral consists of a normal field, a field that's normal to the surface. Okay. I'll draw a little normal that points from 2 to 1. Okay, that's my little normal vector. So if this desk were it, here's my normal, depending on where I make my measurement. That's my normal to that. And so across here, my electric field will be the normal component dotted with minus normal here and positive normal there. But the length of those are going to go to 0 because A to D and B to C are going to go to 0. So my 4 lines here are now going to be turned into 2 lines. The electric field on this level, on this leg, and the electric field on this leg here. Okay? If this and this guy are the electric fields that are normal to the surface, to the boundary, then this guy and this guy are parallel or tangential to the boundary. Okay? So I have E tangential right along the boundary, right along that boundary, E tangential in material 1, minus E tangential on material 2, must add up to my right-hand side is now 0. So E tangential 1 must equal to E tangential 2 across a boundary. So my electric field at the boundary will be, at some point on the boundary, will be sticking up like this. Okay? It'll be sticking up like this. It'll be sticking up like this. Make sure everyone sees me. You guys over there are sort of disadvantaged, I've noticed. We will decompose that vector into one that's tangential and one that's normal. Haven't said anything about what that normal is doing right now. But one thing that I do know is that this tangential component of the electric field in the air above the desk and right in the fake wood just below that surface are going to be the same. The tangential component of that electric field across the boundary is going to be the same. We don't know what's going on with the normal component yet. Okay? But we do know something about the electric field now. Okay? So E tangential 1 is equal to E tangential 2. That's one of the 4 boundary conditions that we need. It comes from one of our four integral equations. This one here. This one here, applied in a very, little case right up from between one material and another material, gives rise to a boundary condition. E tangential 1 is equal to E tangential 2. One of four. Okay, so we've gone back into the macroscopic equations, and we've stolen back the one little piece of the four pieces that we need to be able to move a field across the boundary. Okay? So Maxwell's equations in differential form, 1, 2, 3, 4, along with our boundary conditions, and there'll be four of them before we're done, will allow us to solve, will be as good, will give us all the information as if we were solving the integral equations. Okay? All right. Now, E tangential 1 is equal to E tangential 2. Unfortunately, that's way too easy for us to write. I mean, it says exactly what it means. And that we just can't have that happen in an EMAG class. We have to muddy up the notation to make it sound, more sophisticated and harder. So I'll go back to my n, my normal component, and I'll say if I reference my normal component at that point, and I have my electric field, what operation must I do to give me the tangential component? And that's the cross product. So I can write it as E tangential 1 is equal to E tangential 2. That's kind of the secret way of applying it, right? And then this is the formal mathematically precise way of writing it. But when I look at this, I have to do, n crossed with E1 gives me the tangential component in 1. N crossed with E2 gives me the tangential component. All it is the tangential components are conserved across the boundary. Okay? And that's one of the four boundary conditions. So now we're going to do the same construction that we did before. Same construction we did before, where I have my little loop, ABCD loop. Nice Cartesian, but it doesn't matter because it's all going to be shrunk down to a point anyway. And I'm going to shrink down my A to D going to 0 and my B to C going to 0. And this guy here, this term here will go to 0. Okay? D dot NDA, B dot NDA, d by dt of each of those. Don't care what happens up here, don't care what happens up here. As these guys get shrunk, I'm left with only on the surface. My butterfly net is infinitesimally small. It's not going to capture any of that D field. So this whole term is going to go to 0. Why can't I do that with this guy here? Because I peppered my surface with charge and moving charge. Okay, I peppered my surface with charge and moving charge. So I get rid of all the current that's flowing up here and all the current that's flowing up here, but I still have my delta function worth of surface current. Okay, so there's a peaked distribution of current right at the boundary, approximately a delta function. Maybe some of you remember that delta function will sift through here. And I'll just write that integral as the value of the surface current. Okay? So as I go around that loop, then this guy will just compress to there. This loop here is still 4 pieces. A to D going to 0 and B to C going to 0 means that I only have 2 pieces. A line that goes in this direction and a line that goes in this direction. And so I have my H tangential 1, my H tangential 2. But now this is equal to not 0, but it's equal to the current that happens to live on the surface. So I can write that, and I'll try to be neat. Or I can write it as n crossed H1 minus H2 is equal to J surface. And you should be careful of this minus sign here. The orientation of the normal versus the minus sign there versus the charge or the direction that the current's flowing. So I'm kind of being a little sloppy about all that. So you'll have to be very careful to get your minus signs right on that. Okay? So the tangential components can change for the magnetic field across the boundary. Okay? In other words, if I've got a tangential component, oh gosh, what were my units of H again? What were my units of H again? Thank you. Supposing I have 7 amps per meter, tangential 1, and I've got another 3 amps per meter of current, surface current, then inside of that could well be 10 amps per meter of current inside the boundary. In other words, that surface current can act as a source of new magnetic field. Okay? And remember, that's what that whole equation is doing. Well, we're not as comfortable with that yet. This is the source term, the driving term, the antenna term that gives rise to that magnetic field. So it's only fair that if I have a forcing term in there, that I will not conserve, but rather change the value of the relevant H field. In this case, the tangential component. Okay? We start at 7 and we go to 8:30, is that right? Oh, 8:15. Thank you. I'm glad I asked. It's been a long summer. Well, that should be almost enough time. And you know I don't go over because of the camera. Have you found all the course echo yet? How many of you spent the long weekend watching again and again and again a marathon session? You're too... Hands are up. Let the cameras record that the hands are all up and saying that. So let's see. We have an electric field and a magnetic field across the boundary. Okay? And what we've done is we've allowed us to, 2 equations, we've allowed us to consider what's happening to the tangential component of the electric field and the tangential component of the magnetic field across that boundary. Okay? So that's pretty good. But we also have the normal components to consider. So in some sense, we're only halfway done. In some sense, we have 2 pieces and we need 4 pieces of the puzzle. Or if you want to look at it this way, we have 4 pieces and we need 6 pieces of the puzzle. Okay, depending on how you want to account. But we know what's going on with the tangential component of the electric field across the boundary, and we now know what's going on with the tangential component of the magnetic field. We need to figure out what's going on with the normal component of the electric field and the normal component of the magnetic field. But that's okay, because we still have 2 of Maxwell's equations left to talk to. We've got this one, which is a B dot NDA, and this one, which is a D dot NDA. And I like that dot product with the normal, because that suggests to me that I have of capability of getting to what that normal component that I need is across the boundary. Okay. I came up with a little construction here, that a little loop antenna that I brought into the material and above the material. I straddled it and I let it get close. So I need the same kind of construction that allows me to sample a little bit into the material and a little bit above the material. But I need it to fit. I need to fit a volume in a surface area. I need to drag back my Diet Coke can. Okay? And I need to take my Diet Coke can and I need to put half of it inside the fake wood and half of it in the air. Okay? Well, all this is an excuse for my lousy artwork. There's my surface. Material 2 down here, material 1 up here. I have the normal component as I had before. And now what I want to do is draw my Coke can below the axis and above the axis. So let me draw it in this way, in cross section. Like that. Okay? So my normal component is this way, material 2, material 1. And the little, the time-honored strange expression that you use to describe this is it's a little pill box. It's a little box that you can use to carry around all your pills, your aspirin or something. And so you take your little pill box. Here, I never let it be said that I don't have props for you. Here's my little pill box. And it's sticking halfway into the surface and halfway above the surface. And that's what I've tried to draw here. So I have the integral of d dot n ds across the surface is equal to the integral of rho dv. And this is the same surface, by the way, so it's still got the same js and rho s on it. The important thing is, take a look at the height. That height plays the same role as AD and BC. So I'm going to let my height go smaller and smaller and smaller. So for this very small little pill box, as my h goes to 0, I have d normal 1 times the area minus d normal 2 times the area. That's the left-hand side. I had to think about 6 faces, 1, 2, 3, 4, 5, and 6. But as I let h go to 0, 4 of those faces just went out the window. So I only have the top and the bottom to worry about. So there's my top contribution, material 1. There's my bottom contribution, material 2. Right on the surface, I have the surface charge. And depending on how big this area is, the area goes away. So the normal component of the D field, the normal component of the D field, will change because of surface charge, which to me is only fair, because if I flip back to that, there's my source term to create the D field. So if I've got a plate of a capacitor that I've sprinkled some charge on, and I move through that from one material to another material, well, yeah, my D field should change, and it should change in accordance with the amount of charge that I've peppered onto that surface. So again, the forcing term is doing its job. It's changing the value of the normal of the electric field across the boundary. Okay? So d normal 1 minus d normal 2, the charge makes the difference. If there's no charge, they're the same, but if there is a charge, then there's going to be a difference. And again, we have to write that in a much more mysterious and obfuscating manner. We have to write n dot d1 minus d2 is equal to rho s. At 5 minutes, I've got one more boundary condition to do, right? And that boundary condition is the same construction, but it's now b dot n ds is equal to 0. There's no magnetic monopole. Little fancier way of saying what I said before. North pole, south pole, can't cut them off. So the same kind of situation. But the right-hand side, there's no source on the right-hand side, so that goes to 0. So Bn1 must equal to Bn2, or n dotted with B1 minus B2 must equal 0. So these two boundary conditions are the same, they're just written differently. These two boundary conditions are the same, they're just written differently. Same with that. So I've got one boundary condition, two boundary conditions, three boundary conditions, and four boundary conditions. Now think about what's going on. I have an electric field at a boundary. The tangential component of that electric field, that E field, is conserved across the boundary. The normal component of that electric field, the value of it could change. The normal component will change above and below the surface if there's a surface charge. Okay? If there's a surface charge. Okay? So that accounts for the electric field. Right? The electric field, the normal component will change, the tangential component won't change. We have to think a little bit hard about this E versus D, but for now don't worry about it. There's just an extra little constant term in there that we'll catch up to later on. The magnetic field. The normal component of the magnetic field is the same above the axis and below the axis. The tangential component of the magnetic field can change provided there's a current source. Okay? So with these four boundary conditions, we know what happens to the electric field, and we know what happens to the magnetic field across the boundary. Okay? Keep it in mind, B versus H, D versus E, but I don't want you to mess with that too much right now. We'll get there. Okay? So what we've done today, a little guided tour of Maxwell's equations in integral form. We converted them to differential form so that we didn't lose all the information behind. We did one more little thing with the integral form, and we got what happens at a boundary. So now we are perfectly set to solve differential equations, Maxwell's equations in differential forms, and we can solve them subject to boundary conditions, and we can do so for the rest of the semester. Okay? So on Monday when we come back, I'll go over Maxwell's equations in differential form again, and we'll start down the path of introducing ourselves to other players, other fields of electromagnetics. Have a great weekend.